invitation to speak here. The goal of, I have 3 goals for this talk today. The first goal is sort of a little bit of a review of what has been achieved in the last 4 to 5 years in this domain. Then I want to tell you about some work we've done with my now graduating student Adam Ray and the postdoc Lisa Freihold, which leads to, together with work which was done very recently by Basso and Konchemsky, to what I consider to be a really exciting new test of AdS CFT. And then thirdly, I would like to tell you a bit where we stand. So, oh, this doesn't work, I have to, okay. So anyway, I hope most of you know about this correspondence. So it holds that the 2B superstrings on AdS 5 crosses 5 are exactly dual to this gauge theory. This was conjectured in 1997 by Maldacena and then elaborated by Gabsa, Klebanov, and Polyakov, and by Witten, and it all incorporates important early ideas by, I think, Polyakov and Igor Klebanov. So, and I guess in the first 5 years, this is sort of 10 years old, in the first 5 years, there were sort of lots of what I consider to be sort of non-dynamical tests, sort of PPS quantities. And what we now learned is how to do actually sort of dynamical tests, and they all just work beautifully. So this whole field of integrability and AdS CFT is linked in fascinating ways to many things. So in particular, I mean, you can now really see so that it's really true that the quantum field theory without gravity and the string theory with gravity can be the same, which is philosophically even exciting. It also really demonstrates that the old dream is true, that you can use 2-dimensional quantum field theory to compute in 4-dimensional quantum field theory. You'll see another beautiful example this afternoon by Romuald Janik. And then the whole thing is very interdisciplinary. So it also borders on cutting-edge problems of solid-state physics. And finally, there's very exciting and ill-understood mathematics and representation series of quantum groups and so on and so forth. So anyway, I assume that you know a bit about this gauge theory, sort of the gauge field it shares with the sort of theorems that are used here at CERN to explain the experiments. And basically all this, the matter content is of course different. Everything is in the adjoint representation. You have fermions and scalars in the adjoint, and you can build infinitely new fields from the covariant derivatives. Now all these goodies will be considered some kind of partons, and on the gauge theory side, they are kind of particles which move, as we'll see, in a one-dimensional space. So this is not space-time, and the integrability takes place in this one-dimensional space of these partons. So the action is sort of used to generate the perturbation theory and to do some checks, but it's not been terribly useful for the moment to actually understand where the integrability comes from. So it certainly somehow hides a mystery, and there must be some beautiful change of variables somehow in order to make the integrability manifest, but that's really not understood. So it's a super conformal quantum field theory, the most beautiful gauge theory because it has somehow the most symmetries of all gauge theories. And this global symmetry is called PSU 224, incorporating supersymmetry, conformal symmetry, and asymmetry. Now, the 2B strings, you just have ordinary 2B superstrings in a very, very special background, this AdS 5 crosses 5, which can be, again, defined properly as a coset using, again, this group PSU 224 and modding out with certain bosonic subgroups. So the fermions are not modded out, so they kind of act like staples to tag together the sphere and the AdS space. And then you can write the string sigma model for this. I'm just it's sort of an artist's impression here with only the bosonic part. It was shown by Mitsalf and Zeitlin how to actually incorporate the fermions properly. So basically, it looks like a free series, sort of, but of course there's these constraints, so it's a sigma model, and therefore the quantization of this model has not yet been understood. However, as you'll see below, we are on the way to solving it nevertheless. But again, you could, in some sense, you can ask the same question as on the gauge theory side. This action, or maybe a different action, must contain some secret, because for the moment we cannot really see the integrability. We cannot derive it from the action. Now the duality, of course, you can see in the sense that there's a squared lambda sits upstairs there, and of course in the gauge series the 1 over lambda sits down there, so that's why it's a weak strong coupling duality making it so exciting. Now the spectral problem of the 2B superstrings can be explained as follows. So basically you have sort of angular momenta, 3 of them on the 5 sphere, and they give you 3 conserved angular momenta, which are quantized in the quantum theory in half integer values. And then in the AdS, you also have 2 similar spins in the sort of directions. This is Z1 plus other 3 directions. But then you also have sort of another circle here, which is considered to be time, and you have to measure 1 more charge here. Now, in order to really get something that's not quantized, because the energy of these strings is not quantized in the sense that, by quantized I mean it's not an integer or half integer, you have to go to the universal cover. So anyway, what really ties together the gauge theory and the string theory is this common symmetry, PSU 224. I just showed you, like it appears in sort of conceptually different ways in both models, but it sort of is, it's a building bridge. And you know, it has sort of 30 bosonic and 32 fermionic generators. Now, instead of what you naively would think 8 Cardan charges, there's actually only 6. You have to get rid of a so-called central charge and some hypercharge. And then the 3 remaining Cardan labels are precisely these sort of angular momenta I just explained. I mean, the energy in the time direction, 2 spins on AdS, and then 3 spins or angular momenta on the 5 sphere. As I already argued, that if you look at the string spectrum, then J1, J2, J3, S1, S2 are quantized and stay. They don't depend on the coupling constant, but the energy depends on the coupling constant, leading to this interesting spectral problem. So that's what we want to compute, and we want to show that this energy is the same on the string and the gauge side. Now there's a sort of a conceptual, very deep problem here, because this system, I will show you then that there's this sort of emerging condensed matter system and spin chains and so on and so forth and integrable sigma models. But there's one very big difference compared to the ones that have been solved in the past. Usually in a sigma model or some spin chain, you have sort of the symmetry of the spin chain or the sigma model, and then you somehow have the energy and you try to compute it. Here, the energy is really part of the symmetry. That's an important thing, and therefore it's sort of a little bit mysterious, because in some sense, if you did properly the representations here of this group, the spectrum should pop out, but we don't understand how this works. Anyway, in the gauge theory side, the analog of the spectrum are the so-called dilatation or scaling weights, so they can be seen in the fall off of the 2-point functions, and basically, you look at local composite operators, where now we come to these patterns I showed in the beginning. The things you see in the action, they sort of get pressed together into a space-time point, and you make some gauge invariance by taking a trace. And then you have to really take proper superpositions of these guys to get a good eigenstate of the dilatation generator, so you have a huge mixing problem. And the precise statement is that if you take the dilatation generator, you should extract in a sort of a linear problem, precisely this fall off in the 2-point function scaling weight. And this is this quantity which depends on lambda. And now really AdS CFT says that string energy equals scaling dimensions. Actually, there's also a little subtlety here, because the way the string energy is usually defined and the way the dilatation weight is defined, you have to sort of make a global SO2 for symmetry transformation, so there's some little subtlety here, but at least the statement for the moment is that this is supposed to be exactly true, that the string energy up to this maps, and in the end the labels are supposed to be the same, and you get the scaling dimensions. Now let's come to the integrability. So what do we know? The solid fact number one is that it can be shown that this AdS 5 cross S5 string sigma model, including the fermions, that's the important thing, is classically integrable. That was shown by Wiener, Polchinski, and Reuban. And then a little later, it was actually completely solved, the classical model, by Kazakov et al. And the solution takes a form of a so-called algebraic curve. That's a sort of some Riemann surface with 8 sheets. This is somehow related to the fact that this is an 8 by 8 matrix, this PSU224, so 8 sheeted Riemann surface with lots of cuts and poles, and each such Riemann surface describes some particular rotating classical string solution on AdS 5 cross S5. Now the second solid fact is that if you look at the full one-loop dilatation operator of n equals 4, it can be mapped to a quantum integrable spin chain. That was first understood by Minna and Zarembo in just a scalar sector, and then by us for the full model. And this quantum one-loop integrable spin chain can be completely diagonalized by the so-called Bethe Ansatz. So there's no doubt about this, so it's the other solid fact. Now everything in between, the link now between this one-loop gauge theory integrable quantum spin chain and the classically integrable sigma model is sort of much more murky. And we did sort of little explorations to 2, 3, and up to 4 loops on the gauge theory side, and 1 loop and maybe 2 loop on the string side. Every test that was ever done sort of indicates that indeed the integrability survives, but we certainly don't understand why, and we don't have any proof. Okay, now in the gauge theory, I already told you come to this mixing problem, so let's actually take a concrete example, the so-called twist operators. These are very important because they are kind of very close to the things you actually also have in QCD. So let's take one complex scalar and a covariant light cone derivative and look at these twist operators defined here. Then you can now really see the spin chain because the scalar fields are considered as sort of a one-dimensional lattice. You take a trace to make it gauge invariant, and then the covariant derivatives are like particles hopping on this lattice. Okay, so that's a picture. Now we scatter these particles. That's a scattering problem. And now at one loop it's the nearest neighbor spin chain, but at higher loops it becomes long range. And there's a very beautiful concept called asymptotic Bethe Ansatz that says that even in this long range interaction you can define an asymptotic S matrix, but it's really this one-dimensional S matrix here. And you can write a so-called Bethe Ansatz that says that the phase shift by one such particle, one covariant derivative, when you take it around the trace, the ring, is given by two-body scattering process with all the other particles. So these PKs are lattice momenta of these d particles in this spin chain. So this so-called factorization, that it's all 2 by 2 scattering only the full S matrix, that leads to the integrability. Now, because of the fact that we have a long-range spin chain, at some point you expect a problem when the range of the interactions, the order of perturbation C, gets larger than the ring, and that's a so-called wrapping problem. And therefore, you wouldn't expect this Bethe Ansatz to be completely exact. Now, this S matrix, after the work of lots of people, was actually finally completely found, including the so-called dressing factors, phase factor in front of the S matrix. It satisfies, it's unitary, satisfies the Young-Baxter equation. It satisfies an additional relation conjecture. We don't have any proofs because we don't know what the antiparticles are, but Yannick argued that there should be antiparticles. So there's also this crossing relation. And then Niklas showed that there's this it falls apart in terms of its symmetry into the symmetry of the S matrix is SU2/2 squared times the stressing phase. And the same structure was discovered also on the string side, in particular work by Arutyunov, Frolov, Plevka, and Samakla, and further papers by Gleb and Sergey. So we have the same structure here. Now, diagonalizing this S matrix leads to the so-called asymptotic all-loop Bethe equations, which I guess you've seen before. So basically, here's a stressing phase. You have to solve this equation to diagonalize some particular operator. All these occupation numbers tell you how many particles of various types I have in the spin chain. And then the final anomalous dimension is extracted as a linear superposition of this dispersion law, which is in this x plus, x minus variable written like this. But here's this famous square root formula, which also you've seen in Juan's talk. So that's supposed to be the full asymptotic spectrum. Now there's a very mysterious connection to the Hubbard model. There's 3 points about this. So first, the dispersion law, the one with the square root, is exactly the same in the Hubbard model. Furthermore, this S matrix, these two SU2/2 factors, each of one is a so-called Shastri R matrix of the Hubbard model. And the third thing is that there's one way to write down the stressing phase, which involves commuting charge expectation values that sort of exactly like in the Hubbard model, except you have sort of not Fermi statistics, but Bose statistics. But it's not really understood why there's all these similarities. Now, finally, you can really do something interesting with these twist operators and get a beautiful test of these asymptotic equations. So what you do is you take the number of covariant derivatives very large, so go to very, very large spin. And then it's in any gauge theory, you expect that then the anomalous dimension, quantum minus classical, scales like a logarithm of the spin times some function of the coupling constant. And this function f also appeared in Lance's talk. I mean, this is an artist's impression. He gave you a more precise formula. So roughly speaking, it appears in this exponential formulas for 4 and 5 gluons. And therefore, it's a link. It's a first link between this sort of space, internal S matrix and the space-time S matrix. And you can now use these asymptotic equations, which are very complicated and nonlinear. So linearize in this large spin limit, and you can just find an integral equation, which I wrote here. It's a linear integral equation. I'm not writing the kernel. It's very messy. And then when you solve it and plug for this density, evaluate this density at 0, you get precisely the scaling function. And so that was spectacularly confirmed using these gluons, using the links to the gluon amplitudes 2 years ago by Bernard, Chacon, Dixon, Kosovo, and Smirnov, up to 4 loops. Actually, they only have it numerically improved by these people, but it really, there's no doubt that this is correct. At the same time, starting with work of Gabsa, Klebanov, and Polyakov, who did the classical string configuration for these operators, and then 1-loop corrections here, and later 2-loop corrections here. We also know the function on the string side to 2 loops. And it was also sort of less than a year, last fall, it was shown by Basu, Korzemski, that if you solve the equation at strong coupling, which was very, very hard, it took a year to do that, actually, that it's exactly the same thing comes out. I mean, just analytically precisely. So it has no doubt that this thing is just exactly true. There's a very interesting structure in the coupling constant plane, because if you look at both the dressing phase and then also this scaling function, you see that there's infinitely many branch points on the imaginary coupling constant action, explaining the essential singularity on the string side. But we have complete analyticity on the gauge side. That's why if you sort of have an all orders result on the gauge side, you're done. Just like was always a dream of the planar limit. So now I invite you, the Feynman diagrams for 5 loops were written down. I invite you to evaluate them. That was not done. And compare to the 5-loop prediction of the equation. And then you can try to do a 3-loop computation string theory and also check it against the equation. But that's, of course, all very tough. So we should maybe find other tests of this equation. So here's another one. So basically, let's look at the fine structure of these twist operators. And I told you that the spin chain picture is such that the Zs are sort of lattice points and the covariant derivatives are like particles on this lattice. Here's the Bethe Ansatz describing the motion of the Ds. Now, if you look closely at these Bethe equations and their polynomial structure, you find that there's actually sort of additional lattice momenta or Bethe rapidities more than there's D particles. And in fact, these extra solutions correspond sort of to the motion of the z's on the d's. You can sort of think of turning the thing around, that the z's are also moving on the z. So I'm inverting sort of the spin chain. So now the z's are the particles and the d's are sort of the background. And then you can you get the following picture in this Bethe rapidity plane. The magnons, so the d particles, are sitting here. Then you have holes, these z particles. And for the ground state, you have two very large holes, and then a sea of small holes. So you actually can write sort of dual Bethe equations just for where now the z particles are scattering. And then now the z particles, so here's the d particles scatter with rational S matrices. In the dual Bethe Ansatz, the z particles scatter with sort of gamma matrix like S matrix elements. And the same is true. So for the magnons, the d particles, you have sort of a rational dispersion law at one loop. But for the z particles, you have the psi function, which is the logarithmic derivative of the gamma function as a dispersion. That's actually not completely true. There's a sort of very slight vacuum polarization. You cannot completely exactly turn it around because somehow the d vacuum is not such a good vacuum as the z vacuum. But it's almost true, in particular, in the large spin limit. And actually, there's in this dual picture, there's something very interesting, because then you can see when you turn it around and say then now you can also understand why twist 2 is very, very special. Because if you turn it around, you sort of have only two particles, and the two-body problem is always solvable. So that's why the twist 2 case is much more solvable. We call it hyperintegrable than the general twist case. And actually, my two students, together with Kotikov, recently managed to actually prove this Lipatov, Kotikov-Onishenko formulas from the Bethe Ansatz, which so far was always only done numerically. For the twist 2, this hyperintegrable case. Okay, now you can also look at the dynamics. You can really now look at the dynamics of these small holes and get a refinement of the scaling function. So basically, you can now write integral equation describing the distribution of these small holes, which I wrote here. And there's a new limit now, namely when the number of z particles over the log of the magnon number is held fixed. Let's call it little j. Then there's a new scaling limit. And you can define a generalized scaling function that not only depends on g, but also on this new parameter j, where j3 over log S1 is fixed. And now you can use this kind of picture of magnons and holes to use the asymptotic equations to get an integral equation for that. And interestingly, somehow, when you go to higher loops, at one loop you can completely decouple the magnons and the holes, and you can give alternative description for some reason which I don't understand very well. If you go to higher loops, somehow you cannot really decouple it. And if you want to do the limit, it seems like you need to also look at the holes and not just at the magnons. Anyway, then you get in the end of the day, to spare you the details, it's very technical, basically an equation that looks just like the one for the usual Caspar-Nemmons dimension with a more complicated kernel. It's a mess. I'm not writing it. Okay. Now, the very interesting recent development is the following. So it was actually this limit was also studied by Frolov, Tirtio, and Zeitlin, and Reuben and Zeitlin on the string theory side. So there's results again up to 2 loops actually. And then Alde and Maldacena made a very interesting proposal. Said this new limit can be, in this new limit at strong coupling, an O6 integrable sigma model appears on the string theory side. And that the physics at strong coupling can be understood by doing the thermodynamic Bethe Ansatz for this integrable O6 sigma model. And now what we've done here with our equation, the one I just showed you, we basically summed up again perturbation theory, because we just really used all these expressions which are convergent at small g, and then we say, okay, it's convergent, so it should be valid in the entire coupling constant plane. So in this ON model structure should emerge from the equation if AdS CFT is right. And that was checked in a very beautiful paper recently by Basso and Koshemsky, so it's just 2 months old or so. And they just show that from our equation, when you go to strong couplings, these TBA equations used by Alde and Maldacena just come out. And actually, the free energy of the this O6 sigma model is precisely, essentially, you have to subtract the usual cusps on normal dimension is this new scaling function. Okay, so this interpolation really works. And another really interesting thing is that this twist operator, you only have one scalar particle Z. So you see nothing of the O6 symmetry. At one loop, you just have an SL, what's called the SL2 sector. It's an SL2 symmetric spin chain. And then, if you write this all of Bethe and that's got to strong coupling, suddenly you see that the model still knows about the full symmetry and the sort of O6 is restored. Okay. Now, nevertheless, even though that's all very nice, this Bethe ansatz is not completely correct. And in fact, because of this problem with the wrapping, if you plot number of loops versus length of the spin chain, for a given fixed length operator, you can only give a finite number of orders of perturbation theory. And then when the order of perturbation theory is too high, it breaks down. And this afternoon, you will hear some very beautiful progress that actually for the simplest case, and actually all these things there's infinitely many states in all these boxes, but for the lowest state in this box, Romuald showed actually how to surmount this problem. And in fact, and that's very necessary because we really only have sort of half the spectrum. That has become also clear maybe about 2 years ago. There was a paper by Schäfer, Nameki, Zamakla, and Zarembo which showed on the string side that the asymptotic Bethe ansatz has some problems, and also the Magnon, giant Magnon dispersion law was finite size corrections were worked out in this paper, and then checked in this paper. And there was also a problem with the asymptotic Bethe ansatz. And we also, last year, we checked using BFKL equation, I don't have time to explain this, that the predictions at 4 loops for twist operators are also not consistent with high energy scattering. So really, the asymptotic Bethe ansatz is so only halfway correct. But for new ideas about how to surmount this, we will have Yannick's talk later. Anyway, I have like 5 minutes, so I started. I mean, I started very late, so. So anyway, I think apart from actually solving it, and it's very likely that the thing will be solved before we understood what we have been solving, we should really understand what we are solving, have been solving, and are continuing to solve. What are we actually diagonalizing? We don't even have the full two-loop dilatation generator, only in some sectors. We don't have the full thing. So what is this system? How does it emerge from the gauge theory? How does it emerge from the sigma model? And also, it seems like that this spectral problem is really only a small part of a much bigger story, because there's also these gluon amplitudes. We heard many talks on this, the Wilson loops, and the high energy scattering, and all this is related. That's become clear now in the last few years. And then actually one can even dream of sort of non-planar correction, because there's this other symmetry which is completely killed in the large n limit, so maybe that will help. Anyway, actually integrability and spin chains first appeared in the high energy scattering context. And now we are starting to see that it looks like almost there is some sort of spin chain really for these gluon amplitudes, but one has to find it. We heard some talks about this. And actually, Lippertov very recently showed actually that in the radial limit of the gluon amplitudes, the paper to appear, so an integrable open spin chain appears. So one wonders whether or not, even without this radial limit, there just is some spin chain somehow for these amplitudes. Anyway, then there's this other system, which is so new that we had heard very little now in this conference, but I'm sure we will hear a lot in the next conference. So this planar AdS for CFT3 system. It has evolved very, very fast, and the reason it has evolved so fast because people just basically believe it's integrable, and then they just take any sort of paper that was written in the last 5 years on AdS 5+5 and try to rewrite it for AdS for CFT3. But it's going a little fast, so actually one should cool down a bit and actually do some solid work here, because so what Minna and Zarembo showed, that in the scalar sector again there's a one loop integrability, but it wasn't really shown for the full model that it's one loop integrable, and certainly there was no two loop test even. And also the Lux pair was shown by Aratyunov and Frolov. So it's kind of shown that it was classically integrable. But is the model quantum integrable? Nobody knows. And the Gromov and Vieira suggested some Bethe equations which sort of look like our equations, basically with some very small changes. And, but it's really a debate among the experts right now whether these are correct and in what sense they are correct and so on. And Juan showed you that there's a funny unknown function in the dispersion law. So it seems like there's some really sort of differences, and I hope it's not all a red herring, one has to see. But if it is also integrable, it's very beautiful because it will give a completely new system. It's sufficiently different, that's clear, to be exciting. And actually then one could wonder that the model must somehow use the same trick in some way. And that might actually help finding the trick, because I tried to explain it that we certainly haven't really understood the trick of AdS in the AdS5 case. Okay, now I just make a little bit of publicity in the end of my talk. So actually, this integrability story has become what I think is a kind of important subdiscipline of string theory. And we've actually started in 2005 some sort of conference series on this, first in the Summer Institute in the École Normale in Paris. And then next year there was a conference in Paris on this. Last year again, in Potsdam on this, and last year again in Paris. And this year we had this conference in Utrecht. So organized by Gleb and Fernando Alday and Bernard de Witt and Stefan van Doorn. And we are really trying for the moment, we would like to make it a continuous activity. And in fact, next year this conference will take place in Potsdam again, and it will probably be the week after Strings 09. Okay, and finally I'm finishing. The outlook is there's a unique chance to participate. There's lots of young people here, so please help, in the first exact solution of a four-dimensional Young-Mills theory. Thank you.
Questions?
I have a couple of questions. First of all, you didn't mention at all the OP coefficients. Does it really help in understanding?
Yeah, very, very good question. There was very, very little work was done. I mean, you mean the structure constants, right? Yeah. That's something for the future. I mean, that's why we started this conference series. I think we will not run out of topics soon, because one could wonder, it has been very often said that this should be somehow related to certain correlation functions in the spin chains and so on, but certainly almost nothing was done. It's a very exciting field for future research.
You mentioned that for Planar N, you expect the SL2 to reappear. How does it, do you have any opinion about
No, I'm just saying that it's funny. I mean, somehow this N equals 4 model is the most beautiful gauge theory, has all the symmetries. And then somehow you kill one of these symmetries, the SL2Z, and then somehow the integrability appears. So somehow you kill something, you get something, but so maybe you lose the integrability, but maybe you can use the SL2Z somehow to then make progress for understanding the 1/n stuff. I don't know. It's just somehow it's based on the fact that somehow I've lost something and I've gained something, and this is curious. So. Yeah, that we showed in our original paper with Charlotte Christensen and Nicholas Beiserman on this dilatation operator. We actually looked at the dilatation operator philosophy can certainly be used beyond the large n limit, and one can just show that in the usual sense of commuting charges, these commuting charges would make it integrable into the planar limit. They stop commuting. That's what we showed. But maybe there's something else that I don't know.
Any further questions?
Does your analysis include multi-trace operator?
Well, that's the same question. I mean, because that wouldn't be the planar limit. I mean, it's sort of, if you look at the multi-trace operators and you have a mixing, then what you get is a sort of a gas of spin chains, right? Because each spin chain is a single trace. And now the spin chains can sort of float about and join and split and so on. So it's a new problem. Maybe solvable, maybe not. I don't know. Work for the future.
Okay. Any more questions? If not, thanks again.